Our final speaker of the session is Antonio Franchi. He's a professor here at the University of Twente in the Netherlands, as well as at Sapienza University of Rome. And he's going to close out our session on aerial robotics. So please, Antonio.
Thanks for the introduction. Thanks for the invitation. It's really a true honor to be here. And it's also an honor to represent our group. These are the people. This is a snapshot of the current people working on air robotics at the University of Twente and Sapienza University of Rome. So what do we work on? These are our main research lines. We work on physical interaction for inspections, doing aerial manipulation, and we design our robots and our controllers and validate them and learn gain new knowledge through this type of experiences. We work on perception and actuation constrained multi-rotor control, taking into account all possible sort of constraints that this type of platforms have and their dynamical model. And also we work on cooperative air transportation and manipulation of big loads where multiple aerial robots have to be used in order to face the difficulty of manipulating large objects, for example with cables. We also work on human-robot aerial physical interaction, where human operators can directly interact physically with an aerial robot. We work on trajectories to be optimized in order to be robust to model uncertainty, which is very important in the case of aerial robotics, where aerodynamics plays a big role. And we also work on the design and control of different non-conventional multi-rotors, for example, morphing and omnidirectional and many others. And last but not least, recently we also started to work on aerial manipulation of deformable objects, so objects that have an infinite state space. So what are the research challenges and how they emerge in aerial robotics and in particular in physical air robotics? So as you have seen in the last 10 years, there have been a paradigm shift from contactless aerial robotics to physical aerial robotics. So this, of course, has huge amount of applications and also a huge economical impact. I'm sure it's going to have in the future, and also social impact because we are going to improve the safety of humans working at height and also improve the rapidity and effectiveness of many tasks that are dangerous and slow and they have to be performed in the air. So research challenges in robotic control, in my view, they typically appear in two cases. When you have new hardware, so you need a new equation for modeling the actuation, motion, and measurement phenomena, or you have new physical tasks that are demanded for some reason, and then you have to use a certain hardware to achieve the same some new physical task. But these two things have a mutual influence with respect to each other. So new hardware triggers the possibility to do new physical tasks, but also the new physical task calls for new hardware to be investigated. So in aerial robotics and physical air robotics, I think there is plenty of possibilities to actually do research, groundbreaking research, and at the edge of knowledge, because new sensors appear constantly, new actuators and very difficult to model actuators are present. I want to remember you that in standard humanoid legged robots, for example, or standard mobile robots, you only have actuators that are encompassing two domains, electrical and mechanical domains, while aerial robots, especially if they have to do physical operation on the environment, they have to cope also with the aerodynamical domain, so with fluid dynamics, which is not fully understood, and especially it's very hard to use in order to our knowledge on this domain in order to perform robotic tasks. And also, there are plenty of non-conventional and still not fully explored platforms in this domain. And we have a survey on this on the International Journal of Robotics Research, which recently appeared just a couple of years ago. Also, there are plenty of aerial physical interaction manipulation tasks that have not been solved at all, especially outdoor in the presence of wind. And there is also a survey on tensor transactions or robotics that recently appeared, if you're interested in the topic. By the way, co-authored by Hannibal, who just presented. So I want to conclude this short keynote with 3 simple lessons learned. And in order to give you this, my insights on these messages, I will start from a ICRA paper, which is in line with the subject of this event, which is an ICRA paper from 14 years ago. It's called "The True Role of the Accelerometer Feedback in Quadrotor Control" by Martin and Salaun. So I will try to explain very briefly what is the idea behind this paper. So if you use an accelerometer on board of a rigid body, and this rigid body has no acceleration, then you can use translational acceleration. Then you can use the measurement of this accelerometer as an inclinometer, so to measure the angle, the attitude of this object. You can, for example, close the loop from the sensor reading, what I call the pseudo-angle reading, in a standard, for example, P controller, and this will work. Will control the attitude of this rigid body. If you can, for example, actuate the angular velocity of this rigid body. But now, when you put an accelerometer on a quadrotor, this quadrotor, the dynamics of the quadrotor is such that when you compute the pseudo-angle, you will have a measurement that is constantly 0, okay? If you don't know that, and the researchers didn't pay attention to this, or practitioners didn't pay attention to this in the early age, actually the first 10 years of quadrotors, quadrotor research, then you are closing, and you think you are closing the loop with this angle measurement, pseudo-angle measurement. Actually, you are closing the loop with a measurement which is always 0, so it will never work, okay? However, it works, and people never bothered about this fact, this apparent inconsistency. So in this paper was really insightful for me because it showed that if you actually extend the model of the quadrotor, so you gain more knowledge about your system by modeling, and you include the quadrotor, the rotor drag of the quadrotor, then you can see that actually this pseudo-angle measured through the accelerometer is actually a measurement of the velocity of the quadrotor. And so what you are doing by applying a P controller is actually a P controller on the velocity. And it happens that actually the system is asymptotically stable, and you are controlling not only the angle, but also the velocity itself. And this is the reason why it works. So lesson 1 from this. Solving a problem for me is not enough, okay? You can have a manifestly bad design which can result in something that works. But something that works doesn't necessarily mean that you have understood the phenomenon. Lesson 2. The accelerometer on a quadrotor doesn't measure the acceleration, doesn't measure the angle or the inclination. Actually it measures the velocity. So the measurement of a sensor depends on the dynamics of the system on which, the interpretation of this measurement actually depends on the dynamics on the system on which the sensor is embedded. You cannot consider the two things separately. So look at the nature of real things, not just at their label, or what is on the box when you purchase them. And models are your friend in that. Third lesson, let understanding be your goal. Okay, for many years, people didn't bother about this inconsistency because they considered the problem of stabilizing a quadrotor was solved. Okay, the system worked well. So who cares about the fact that the model is everything is inconsistent? But this is just a partial achievement for me. So don't let partial achievements kill your curiosity, and be suspicious of solutions that work without that you understand why. And I want to finish with a paraphrasis of this famous quote, which has been presented already a few times in this event, which is all models are wrong, but some are useful by changing it, actually. All models are wrong, but some work when combined together, and there is another model explaining why. Thank you for your attention.
Thank you, Antonio.